one as well as your loved ones. The Lord is risen. Alleluia, alleluia. Truly he is risen. Alleluia, alleluia. All right, guys. So, questions. You had a couple of questions about heat exchange. Any questions? Madav?
Can you show us how to convert watts to joules in proper notation for number 33?
Okay, except 23, because I forgot to teach you like power. I will do that today. So except 33. All right. So we're looking at 30, 31, and 32. Yeah. So 30, 31, and 32. Are we good? We're good. Okay. So who's this, Madav? Like Aristotle? I have no idea. Who's that?
Archimedes.
Oh, I see. Ernest is late. Okay. So let's start here. So I'm happy like no one got does have answer for does have questions for the first three. Okay, so let me share this here. All right, and then you'll be able to do a 34. I apologize for this. I forgot to teach you power. There we go. Okay, so let me teach you a power, which I forgot to do. So power. So the symbol is B. So put this on this side. There you go. Okay, so power is the rate at which, now there's a little dot here. Okay, let me sort of put it a little bit higher up. All right, so it's the rate at which work is done or heat is transferred. Actually, this is not very good. Heat is transferred because heat is a transfer of thermal energy. So I should say the rate at which thermal energy is transferred. But anyway, or now this is going to be like a little long here. Or the rate at which energy is transferred transform okay, generated, produced, used up, consumed, dissipated, etc., etc. All right. So all of this here. All right. All right. So with respect to time. All right, so power is the rate at which work is done, heat is transferred, or energy is transferred, transformed, generated, produced, used up, consumed, dissipated. There's a lot of different terms here with respect to time. So basically, formula is this. First one is this. So power is work over time. The second one here is this one. And this one here is this. So this is the most general one here. This is the most general. Okay. We know that work is a transformation of energy anyway. The same thing with this, but for thermal energy. So this is a general here, right? This is all general. Okay, so whoops, the unit of power. Well, this is like joule per second. And joule per second is a watt. All right, so 1 watt is 1 joule per second. So the unit is the watt. Okay. So example, let's see, 12-watt light bulb consumes 12 joule of electrical energy every second. Every second. All right. So we're gonna when we do electricity next, very soon. We'll start like next week actually. We'll do electricity, we'll do power, and this is exactly what it means. So electrical devices have a power rating, and the power rating tells how much electrical energy is being used up every second. Okay, so let's do another example here. So a box is pulled horizontally with a force of, let's say, 30 Newton over a distance of 2 meters in, let's say, 5 seconds. So find the power delivered by the pulling agent. All right, so okay, so people are late. All right, so the box is pulled horizontally. Sorry, guys, horizontally, with a force of 30 Newton over a distance of 2 meters. In 5 seconds, find the power delivered by the pulling agent. Okay, so that's pretty easy here. FA, of course, is 30 Newton, the applied force. We're given, of course, the distance over which the force is applied, and we're given also the time. And what we're looking for the power. by the applied power. Okay. Well, this is going to be equal to the work done by the agent here, the applied, the pulling agent. And we know that this is equal works is the force times delta T times cos. Of course, here it will be like 0. And then you just put the values. So it's like 30 Newton times 2 meter times 1 over 5 seconds. So the top one will give you like 60 joule per 5 seconds. So the power output of the pulling agent in this case will be 12 watt. Hey, look at that, 12 watt, like my light bulb. All right, so this is the power generated by the pulling agent, 12 watts. So this pulling agent exerts, outputs 12 joule of mechanical work, all right, for every second, right? Every second. All right. Okay, another quick example here. A burner is, let me sort of write like a bit better here. There you go. A burner is rated as, let's say, 120 watt. Find the thermal energy produced by this burner in, let's say, let's say in 10 minutes. All right, so we leave this burner, could be on a stovetop here. There's a burner here, it's rated 120 watt. And how much thermal energy is produced by this burner in 10 minutes. So once again, it's not terribly difficult here. What do we have? We have the power, which is this. It's a capital W, by the way. It's the same as the symbol for work. But work is joule, right? The unit of work is joule. The unit of power is watt. What we have also the time, 10 minutes. But of course, we need to convert this into seconds. So times 60 seconds and per minute, and I'll give us 60 seconds. And what we're looking for this. So we just use the formula here for, it's a little laggy here, but it's coming, right? So just use this one. Because Q is a transfer thermal energy. So we just use this formula here. And then Q is equal to power times delta T. And you find like 100 watts times 600 seconds. And so 100 joule per second, you remember. And of course, the second here goes away. And that gives us 36.00 joule or kilojoule. All right. Okay. So this is how much thermal energy is produced by this 120 watt burner.
I think it's 72,000, sir.
What's that?
I think it's 72,000.
Oh, 72. I'm really, thank you. 72. Thank you, Max. Really rusted, mentally. Getting old here. All right, so 72,000 joule or 72 kilojoule. You good? Everyone is good? No, no hands up. Okay, Madav gives me a thumb up. Okay, so with this, you should be able to do like 34. If you haven't been able to do 34, is it 34? 33, 33. So now you should be able to do 33. And I apologize for this. All right. Okay, so there'll be like the title here. I'm not going to put it yet. Put it in a few seconds. Really have to find a way to make a line. It should be like a nice line. All right, so consider worming. Oh, there's something I forgot before that. Sorry, guys. Sorry. I know it's easy for me to do that. Okay, before we get there, sorry. Remember here, Q is equal to MC times delta T, where C is the specific capacity. But sometimes it can be written as this. This is a big C here. Okay, so where C, big C, is called the heat capacity, not the specific heat capacity. So it's called the heat capacity. And in this case here, the heat capacity is nothing else but the specific heat capacity times the mass. So in other words, the little c here, the specific heat capacity is the heat capacity per unit kilogram, per unit mass. That's what it is, okay? All right. And of course the unit here, so unit will be unit for, whoops, for big C is of course joule per second, joule per, per Celsius, right? Is that okay? Now, if we go back, oh, I put it on a scrap. Oh, it's not supposed to be the scrap one. Anyway. All right. Okay, so let me close this here. I'll come back to this yesterday. Natalie, by the way, Natalie, was it correct here, or did I make a mistake again, or?
Oh yeah, I accidentally read my number wrong.
Oh, okay. So it was okay. Yeah, okay. Thanks. All right. So you remember yesterday this problem here? Whoops. I have to go back here. All right. Remember here you had like this this piece. It's getting there. It's a little laggy here. Blah 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 blah. There we go. So remember here, so you have your gold coin here. You put it in an iron container filled with 100 ml of water. And then, so it's all isolated. We'll put this in and ask you for the final temperature. So of course you use the heat exchange energy, heat exchange formula. And we had this because the colder bodies were the water and the iron. And remember here, like delta T, the change in temperature of the water and change in temperature of the iron were the same. So we could sort of factor this out. All right, and this is what we did. This is what we did right here. We factored this out, right? Time delta T. Well, this thing here, this is the heat capacity of the system of the iron container and water, right? So this is the heat capacity of this system here of the iron container and the water. So when we calculated this, remember, so you can see here like the number right here, 1798 joule per second, per Celsius. So this is a heat capacity of this iron container plus water combined. That's a heat capacity. So that would be like big C here. Okay. All right. So I have to go to scrap and then I have to change it. All right. A couple of things here. 1 calorie. 1 calorie, or 1 cal, is the energy needed to raise 1 gram of water by 1 degree Celsius. And what is this equal to? Kilogram joule per kilogram. So 1 kilogram is 4180 joule, right? So if you have 1 gram, it'll be equal to this. I think so. Okay, let me sort of double check here to be like really sure. Yeah, Catherine.
I think you forgot the K in front of the gram.
No, I think it's 1 gram. I mean, yeah, that's what I want to check here.
Okay.
So hold on a second here. So let me check this like very carefully here. Calorie. Yeah, it's 4. Yeah, it's 4.8. Yeah, that's correct. That's correct. Okay. So I was not wrong, Catherine. Good try. All right. So it's another unit. Now, remember when you eat a snack or you look at the energy content and it's given in calories, it's not the same calories as this. This is like big C calorie. Okay. So big C calorie. Okay. So for food, the energy content. Okay. They use big C calorie. And big C calorie is equal to, I think, 1,000 cal. Okay. All right. So big cal. So they use big. So when you look at, let's say, a chocolate bar, and it tells you, I don't know, it has like 12 kilocalories, 12 kilo big C calories. This is the chemical, this is the microscopic potential energy of this bar, of this chocolate bar. This is how much potential energy, how much chemical energy is stored in this chocolate bar that you will be able to tap into once you eat it. Okay. All right. So yeah, that's a microscopic. That's the potential energy. Okay. Now that we've done this here, so let's go back to what I want to teach you today. All right. So now consider warming a substance warming Let me sort of write a little bit better here. So consider warming a substance at a constant rate. Right? So what does it mean here? It means that the amount of thermal energy supplied to the substance is going to be, it's going to be done at constant rate. So, so if I have a burner, my burner here, so I have my little burner, 100 watt, and it supplies like 100 joule per every second of thermal energy to the substance. Constant rate. Yeah. Now I'm going to use this, I'm going to use another page because I need like a bit of space here. Okay. So we're going to do a little graph. So here, this is going to be the temperature. And here, this is going to be the thermal energy absorbed. So Q absorbed. All right, or time. Okay, it's the same because here, since we agreed that it's a constant rate here, okay, so what happens here is the Q absorbed is going to be proportional to the time, okay? All right, that's what it means, okay? And then what we do is we keep track of the temperature of the object. Okay, so what are we going to see here? This is what we're going to see, guys. So we're going to start at a certain temperature. And let me put this here. So we're going to, so as you supply more and more like thermal energy as it absorbs energy here, the temperature of the substance will increase. But all of a sudden here, the temperature will stay the same, despite the fact that it is absorbing thermal energy. Now, the fact that the temperature here stays the same, what does that imply? Luke, since you're late, can you answer this? And you didn't unmute your mic? Luke. Nah, don't tell me you cannot chat. Okay. What you cannot? Yeah, Timothy. Just hold on a second. Look, you cannot. Your mic is not functional. Yeah, it's functional. Okay, so what did you say?
Would it reach the same temperature?
Does it look like, yeah, it will reach the temperature. Okay. No. What I'm saying here is this, is that all, so I'm going back to Timothy here. So you can mute yourself here, Luke. Make sure you're here on time next time. Okay, so here the temperature stays the same. So what can we infer from this, Timothy?
So the substance would change state when it releases. So it releases.
You're going like way far. Yes, I understand. But just from what you know, guys, what the temperature stays the same. What can you tell me? Yes, Nadav.
You say that the energy absorbed is equal to the energy released?
No. Okay, come on. What is temperature, guys? What is temperature? What is temperature, Stephen?
Oh, is it just that it reaches the capacity.
Okay, go back to what we know about temperature. That's what I want you to go back to. Jason.
Is it when they reach the equilibrium?
No, no. It's not an equilibrium. We keep like supplying like thermal energy. It's like a burner here. It's not a heat exchange. All right, Catherine.
Oh,
Yeah.
it's gaining kinetic energy.
It's
Gaining kinetic energy.
okay. The temperature
Or
stays.
thermal.
No, stop saying thermal. It's not a heat exchange.
Oh,
Hey,
sorry.
no, that's okay. Good try anyway. Come on, guys. What is temperature? You know what temperature is. Based on what temperature is, just go back to your notes here. What if it stays the same? What can you infer here? Day.
The average kinetic energy per particle can't go any higher.
Okay, so the average kinetic energy per particle stays the same all throughout. The microscopic kinetic energy of the object does not increase. It does not increase. And yet, this object here is absorbing thermal energy. So where's this thermal energy going into? Where is this thermal energy going into? Eric Hugh?
Kinetic energy.
No, no, the temperature doesn't change. All right, thermal energy here, right? Thermal energy doesn't change. The microscopic kinetic energy will not change. Hold on a second. You want to just before David here? Do you want to answer Eric Hugh again? No. Okay, David. No. No. This is like there's no waste here. Jason. Ooh. No?
I was about to say what Burma said.
No. Okay, guys. What is thermal energy? Tell me what thermal energy is. Okay. If you don't answer, I'll choose one person. What's thermal energy? You have to just to study. There we go. Benjamin. No, okay, Benjamin. No, not Benjamin. Benjamin like came on time this time. That's a good thing. Yeah, Day.
It's a sum of kinetic microscopic energy and potential microscopic energy.
Very good. Okay. Now, temperature, Eric Lou. The temperature stays the same, and yet the object absorbs thermal energy. So where is this thermal energy going into? Day.
Potential microscopic energy?
Yeah, the microscopic potential energy of the object is increasing. And the microscopic potential energy is due to the intermolecular forces. You remember? So what happens here is that despite the fact that the object is absorbing thermal energy, its microscopic kinetic energy doesn't change. But what will change? Thermal energy, of course, increases. So it means that the microscopic potential energy changes. What's happening here is that when the microscopic potential energy changes, it means that the forces between the molecules, the tiny particles, are different. Either like the particle are moving farther apart, or the forces here are modified. And as Timothy mentioned earlier, what happens here is that you have a change of state. You have a change of state. So when you have a change of state, let's say here it goes from solid to liquid, the intermolecular forces will change, right? They will change. And as a result, the microscopic potential energy will change as well. Whereas okay, so what happens here is this. So let's say here, this is a solid. So you keep supplying this solid, and then after at a certain temperature here, called the melting temperature of or the fusion temperature of the solid, now the temperature will stay the same because it's starting to go from solid to liquid. Now, when it's fully into liquid and you keep supplying thermal energy, now the temperature will rise again. So here, this is liquid. So what happens here, this is a change of state here, right? So if you go this direction, if you go in this direction here, what is this called, guys? Solid to liquid. Come on, learn this in elementary school. Max?
Melting.
Melting, very good. Okay, when you go from liquid to solid. Yeah, Stephen?
Freezing.
Freezing, very good. And then you supply energy. So the temperature of the liquid will increase. And then at some point, the temperature will stay the same. So what happens here is there's another change of state. The molecular forces here are changing nature, right? Like the nature of the molecular forces are being changed. All right, so now it goes from liquid to, all right, so it goes from liquid, there's more gas, and at this point here, everything is gas. And then if you keep supplying energy, well, the temperature of the gas will increase. All right, so let's look at, so when you go from liquid to gas, what is this called? Leo?
Evaporation.
Okay, evaporation or boiling. Although there's a technical term, there's a technical difference between the two, but that's okay. And when it goes from gas to liquid, not always the same people. Come on. Okay, come on, some other people. Leo, there we go.
Condensation.
Yeah, condensation. All right, very good. Yeah, Stephen.
How does solid to gas work and gas to solid?
Yeah, it depends. It depends on the substance. Sometimes the substance goes from solid to gas without going through a liquid. So an example of this would be, of course, dry ice, which is nothing else but frozen carbon dioxide. And so when you take frozen carbon dioxide and you put it in a room, it goes right away to gas instead of going through a liquid, right? All right, so this one here, this is called the fusion temperature. So we use F. I know it's not final here, it's F. So this is the fusion. Yeah, it's so small. This is fusion temperature. Fusion or melting temperature. Or melting temperature. And here, of course, this is has to be straight here. I'm not doing a good job here. Okay, make sure you mute yourself, guys, because I can't. So this is called TB. This is for boiling temperature or, yeah, boiling temperature. Or vaporization temperature. Vaporization temperature. All right. So the title here was change of states. All right. All right, so each substance have its own Each substance requires like different amount of thermal energy to fully change the state, right? So for fusion, right? So it's like freezing or melting or freezing. Melting. Or freezing. All right, so what do we have here? We have this Q F is equal to this, where LF is called the latent heat of fusion, the specific latent heat of fusion. Specific latent heat of fusion. Yeah. Latent heat of fusion. All right. So if you wanted to, and this is a physical characteristic of a substance, of pure substance here. All right. So, and the same way as specific heat capacity is a physical characteristic of a substance, you have also the specific latent heat of fusion, which is also a characteristic of the substance. All right. And of course, it's proportional to the mass. The amount of thermal energy you need to melt a substance depends on the mass, right? So you require like more thermal energy to melt like 2 kilograms of ice instead of only 1 kilogram of ice, all right? And the QF here is called the latent heat of fusion. All right. Yeah. And now you just stay there. By now you should sort of understand here what specific means. Specific means nothing else but per unit mass. All right. So if you take this, divide by the mass, you get this latent heat of fusion per kilogram, or specific. Right. And then for vaporization. So we're talking about here like boiling, right? Condensation. All right, so what do we have? We have this. It's little v. Okay, so where? So LV is called the specific latent heat of vaporization. Latent heat of vaporization. Have you learned this in chemistry, guys?
No.
No?
Next year.
Ah! Those chemistry courses. So specific latent heat of vaporization. And of course, this one here is latent heat of vaporization. All right. All right, so why do I put an absolute value here? Because to melt, you have to supply thermal energy. So the object, the solid, has to absorb thermal energy. So in this case, QF will be positive. Freezing, in order to freeze something, you need to remove thermal energy from it. So the object needs to lose thermal energy. So in this case, QF will be like negative. All right. So depending on whether the object absorbs or loses thermal energy, it's either positive or negative. All right. All right. So example here. So you have a table too. Let me see here. Move. So water. So example, the latent heat of fusion for water is 3.3 times 10 to the 5 joule per kilogram. Sorry, the specific latent heat of fusion for water is this. So of course it's not per temperature here, it's per like kilogram. So what does that number tell you? It tells you that in order to melt exactly 1 kilogram of solid of ice, right? You need to supply 3.3 times 10 to the 5 joule so that it converts completely from solid to liquid, all right, for 1 kilogram. That's what it means. And it's a lot. So that's why, like, when you boil, like, it takes enormous amount of energy to boil water. And it takes also a lot of energy to raise its temperature too. So it's a very special substance. Yeah, Madhav.
Does it matter the power at which the energy is applied?
What's that?
Does the power at which the energy is applied matter?
Well, yeah. I mean, if you so it's like your stove here. So if you put it on low setting, right, it'll take like a longer time, right? If you put it on a high setting, then like there's more thermal energy being given off per unit time, so it'll be faster. Is that okay?
But the total amount of energy is the same.
Yeah. You need like if you want to melt 1 kilogram of ice into 1 kilogram of water, you need exactly, the substance needs to absorb 3.3 times 10 to the 5 joule of thermal energy. Okay, yeah. Okay, so let's do an example here. So find the total thermal energy find the total thermal energy needed to raise 2 kilogram of ice needed to raise 2 kilograms of ice at let's say minus 25 degrees Celsius to a temperature of let's say 60 degrees Celsius. All right. Okay. So how much thermal energy needs to be supplied? So what you're looking for here, you're looking for Q, right? The total one. And of course, it's going to be positive because it absorbs. Well, there'll be like 3 terms here. First of all, you need to bring ice from minus 25 degrees Celsius to 0 degrees Celsius to its temperature of fusion, right? So once you've raised the temperature of the ice from minus 25 degrees Celsius to 0 degrees Celsius, now you need to melt it. So here it's going to be melting. And then once it's all liquid, now you have to supply thermal energy. Now it's going to be water, of course, like liquid water. Right? Now you need to raise the liquid water from 0 degrees Celsius to 60 degrees Celsius. All right. So you have three terms here. Now, how would we find like the thermal energy needed to raise the ice from minus 25 to 0 degrees Celsius? So which formula are we going to use here? Anyone? Which formula? Leo, you're mute. You're still, your mic is still on. You want to answer, or? So which formula are we going to use, guys? Yeah, look. No. Look. No, Ernest.
MC delta T.
MC, that's correct. So here it's going to be MC, but here it's going to be specific ice capacity of the ice, no, of solid water, time delta T. All right. So here it'll be the temperature of fusion. This is not like final temperature here. Okay. It's temperature of fusion. I'm sorry, like you put this here. Minus, of course, the initial temperature, right, of the ice. Now, next term is melting. All right, so melting. What are we going to use here? Are we going to use the latent heat of fusion or latent heat of vaporization? Latent heat of fusion or latent heat of vaporization? Yeah, Max.
Fusion.
Yeah, fusion, right? So it's going to be the mass times the latent heat of fusion for the water. And then finally, for the next, when it's all liquid, now we go from, we raise the temperature. So it's going to be the mass times the specific capacity of liquid water times, now it's going to be the final. I don't know what I'm going to put here. So I'll put like TT. There you go. Minus the temperature of fusion, right? So where? So TI is, of course, minus 25 degrees Celsius. TT here, which will be the final temperature, will be like 60 degrees Celsius. TF, it will be the melting temperature, fusion temperature of water, which is of water, which is, of course, 0 degrees Celsius. LF is going to be the latent heat of fusion of water, which is 3.3 times 10, and 5 joule per kilogram. The mass is, of course, 2 kilogram. And then the ice. So the heat capacity of the ice, if I'm not mistaken here, I think it's about 2,000. Yeah. Okay, so they give in your book, they give like this. Right? So it's almost like half as much as liquid water, right? So to raise like 1 kilogram of ice by 1 degree Celsius, you need half as much energy as with water, right? And then, of course, liquid water here, right? Liquid, it's 4180 joule per kilogram per Celsius. Okay, well then we're gonna happily put everything in. Now you could, if you want, you could factor out M. You factor out M, you would have all this here, and this would be like, no, it's okay, forget it. Okay, don't factor it out. Okay, so let's put this here. So 2 kilogram times 2100 joule per kilogram per Celsius. Temperature of fusion is 0 degrees Celsius minus, don't forget, right? So here, of course, you raise the temperature by 25 degrees, plus 2 kilogram times 3.3 times 10 to the 5 joule per kilogram. And then plus the last term here, which is 2 kilogram times 4180 joule per kilogram per Celsius. And the fusion, sorry, the final temperature is 60 degrees, right? Minus temperature of fusion, which is 0 degrees, all right? All right. So of course, kilogram will go away. All right, I'll do the BB way here. We'll do it like step by step. So let's do this here. So it gives you like 4200 joule per Celsius. All right, and so for the ice, for this amount, 2 kilogram of ice, it takes this much thermal energy to raise it by 1 degree Celsius, right? And then times 25 degrees Celsius, plus, so 6.6 times 10 to the 5 joule, right? So this is how much thermal energy needs to be supplied to melt 2 kilogram of ice into water. And then finally, so plus, what is that here? So it's 6, what is that? 6, 0, is it 3, 8? Is that correct, guys? Is that good? All right. So, is that good, guys? This one? 2 times 4180. Is that it? Yeah, okay. Times, of course, 60 degrees Celsius. All right, so here's Celsius. And then now it's too much for my little head. Well, not that much. It's like a quarter, 42, well, perhaps. Oh, I'm losing it, guys. All right, so 42,000 times 25. Okay, so that gives you this much joule. So in order to raise the temperature 2 kilogram from minus 25 degrees to 0 degrees Celsius, you need this much energy. Now, once you get ice at 0 degrees Celsius, you want to change it to liquid at 0 degrees Celsius. So, of course, you need this much. And then finally, to raise the temperature of liquid water at 0 degrees Celsius to 60 degrees Celsius, it'll be 80 times 60. So it'll be this much. All right. And then you happily like add all this up. And then you get this much. All right, or sometimes if you want to put it in kilojoule, You put in kilojoule. But anyway, there we go. All right. So in order to raise the temperature of 2 kilograms of ice at minus 25 degrees Celsius up to 60 degrees Celsius, this is how much thermal energy you need to supply. Yes, Madav.
I got a different number.
Oh, did I make a mistake again?
At the end, it's just with the addition, I got 1.2 million.
Oh, this one here? This
Yeah.
one? Okay, like at the end? The last three numbers. Oh boy. Boy, what are we gonna do with me? What are we gonna do with me? Plus 501600. Yes, you're right. Wow, I probably did. So it's 8316. Thank you, guys. So,
And I had another question about the
Thank you.
notation.
is that correct, guys? No? Is that better?
Yeah.
Yeah. Okay. Yes.
When you write the uppercase T in the textbook, it says to use uppercase T for Kelvin and then lowercase t.
Forget about it. That's BS.
Okay.
Okay. We're always gonna use like Celsius anyway. So next year we'll use Kelvin, but not this year. Okay. Yeah, this book doesn't know. Okay, questions? All right. So you'll have like a couple of questions on latent heat. Yeah, sometimes like some people say, well, what about if I don't know like the fusion temperature, right? And I don't know if it melts. Yeah, that's well, you need to know. You need to do a little bit of research here and find out the fusion temperature or the boiling temperature of a substance, okay? So that you know like where there's a change in state. Yeah, Forrest.
Sir, I think the number is still wrong.
Oh, what is it?
It's
Oh, I put like 3.3. Is that it? I
I'm
put
not sure what
3.3. Yeah. Okay. Okay. So 0.1600. Okay. I said this one now. So what's the number, Mister?
1,266,600.
Yeah, this
Yeah.
one, right? Okay. Because I put like 3.3. Okay. Thanks, Forrest. Okay, so yeah, so it's an enormous amount of energy, by the way. If you want to put it in calories, in big C calories, yeah, David, hold on a second here. Big C calories, this would be big C calorie. Wow, you have to divide by 4.10. I don't know. Anyway, you can do the calculation. Yes, David. No. It'll be given. It would be like useful if you could at least know like the specific heat capacity of water, right? 4180. But no, numbers would be well. Water you should know like it freezes, it melts at 0 degrees Celsius and it boils at 100 degrees Celsius, right? So you should at least know these. Yeah, Forrest, do you have another question? No, because your hand is still raised.
No, sorry.
Ernest?
Wait, so if you give us like another material, would you give us like the latent heat? Like,
Yeah, or you just look it up. If there's no information in the book, just look it up.
How about like on a test?
No, I would give you. I mean, of course. I would give you. All right. Okay, so tomorrow there's a virtual staff meeting at I think 11. So I cannot teach you. And I think they're gonna sort of probably leave it at 11 now. on Wednesday, every Wednesday at 11. Before it was at 9, so that's why it did not interfere. But now they put it at 11. So, or at 10, can't quite remember. So what I will do here is that tomorrow we'll meet at 2:30 in the afternoon. Okay. So if they keep like the virtual staff meeting at this time all the time on Wednesday, so on Wednesday we're going to meet at 2:30 in the afternoon. Next, tomorrow morning I will sort of put tomorrow morning, so probably like around 8:30 or so, on my website I will put some additional questions that you need to do. So you can work on that, right, during the day, and then at 2:30 you can sort of ask me questions, okay? So those questions for tomorrow, I mean, you can do them. Like it's about specific capacity, latent heat diffusions, and so on, okay? But a bit more challenging than the one in textbook. All right. So questions? Yes, they.
So, since we're not doing exams, the letter that they sent out said there's going to be a big assignment for every class. Is that going to be our ISU, or is there going to be another one?
Yeah, probably. I don't know. I'll have to wait. Probably tomorrow we'll talk about it, a staff meeting, and I'll let you know as the case may be. Okay? So don't worry about that. Don't worry. You guys all get like anyway, like unfair like marks anyway, so you're in IB, so it doesn't really matter. Max.
Wait, sir, is it true that that our marks can't be lowered?
That's correct.
Really?
Yeah.
Oh, okay.
Why? You want your mark to go down?
No. I'm just saying, like, cause you know, like, cause it wasn't like too high, so you know, like I can only go up.
Well, no, but if it can go up, right?
Yeah, so it's
It
good.
can go up, but it cannot go down. Yeah.
Okay, that's good.
Yeah. Okay. Any other questions? I mean, my point here is for you, like, really to learn. That's my main focus here. You learn, so you prepare for next year. That's my main objective. Okay. As I said, don't worry too much about the mark. In any case, you all get like inflated marks anyway. So, and it doesn't really matter. So what matters is your grade 12 mark. Okay, questions? All right. So
yeah, can we scroll up a little bit?
what's that?
Can we scroll up a little bit?
Because you came in late.
No, because I missed a part.
Yeah, because you came in late. Make sure you are here on
Here.
time, guys. Okay.
Yeah, up to here. No.
Yeah, I know it's laggy, so you have to. All right.
No,
so
I just wanted to see the down a little bit.
Yeah, down a little bit. So I'll see you like tomorrow, guys,
Yeah,
at
right here.
8:30. Once
Right here.
again, like make sure like in the morning tomorrow, probably between 8:30 and 9 o'clock in the morning, I'll put like a some additional question on the website. So work on this, and I'll see you at 2:30 tomorrow. Okay, guys. All right. So bye. And I'll see you tomorrow.